Okay, so welcome to the possible last lesson for the Chem unit in Science 10. For this lesson, you will need to be able, you will need a device that can edit in Google Slides. Before starting the lesson, I wanted to talk about the schedule I uploaded to the Science 10 folder. You'll find that it's called Very Tentative Schedule. And if you click into it, you will find the lessons and a general idea of what your following lessons will contain. And here we have the meeting ID and the password and the link to the Zoom meeting. All right, let's come back here. Now, back to the lesson. First, we'll do a review of some points from the previous class. First of all, if you watch to the end of my previous lesson, and if you remember how Tony was like kind of throwing shade at me for not calling water by water, but instead saying dihydrogen monoxide, all right? He was kind of right, okay, as I hate to admit it, but I'm still gonna say that I can call it dihydrogen monoxide if I want, all right? Basically, what Tony was trying to say is that certain molecular compounds are exceptions to the molecular nomenclature process. These molecular compounds have what we call common names, and you will have to memorize them in your high school science courses. Don't write these down for now because I'm kind of trying to speed through this lesson, but maybe after the lesson, when the slide is uploaded, copy these down and try to remember them. So yeah, these are the molecular compounds names you have to memorize. Well, so for example, water is H2O, sucrose, C12, H22, O11. I'm just gonna move on. In my lesson, I wanted to include a tip for you guys for your high school science course, which is, some of you might have already seen it, which is the ASAP Science Periodic Table song. I recommend, most people will probably remember the song up to the 19th element. There we go. So Zainab, since you're the only person here, do you know what element has 19 protons? For your benefit, I will open up the periodic table. It is not on this one, it's on this side.
Potassium.
Potassium? Okay, yes, you are correct. It is potassium. Basically, memorize the song up to when they sing potassium, and probably all your friends will know how to sing it as well. All right, ions. I don't think in the previous lesson I mentioned why atoms always form ions with a certain charge. For example, where oxygen will always form an ion with only a negative 2 charge. Except transition metals, they can have more than one charge for their ions. Basically, ions want to follow the fastest way they can have a full valence shell. They can do so by either losing or gaining a shell, whichever way is either losing or filling the outermost shell they have. I need to fix that. Whichever way is fastest. Now, on the periodic table, all elements in the same group will form the same charge unless it is a transition metal. And remember that groups are organized by valence electrons. So, for example, when I mentioned that elements will form ions where they will want to form a full valence shell, they can do so by either losing a shell or filling their outermost shell as their current outermost shell. There we go. In this case, hydrogen, the fastest way for it to have a full valence shell is to lose its 1 electron, which will give it a +1 charge. But since hydrogen is special, it can also have a -1 charge, but whatever. All right, oxygen. The fastest way for oxygen to have a full valence shell is for it to gain 2 electrons instead of losing like 1, 2, 3, 4, 5, 6 electrons to have a full valence shell. Therefore, it will form an ion of a -2 charge. The fastest way for a sodium atom to have a full valence shell is for it to lose its 1 electron and therefore lose its outer shell, where in its ionic form, it will now have a full valence shell. Moving on. More on molecular compounds. Firstly, polyatomic ions. I mentioned these in the previous class. Polyatomic ions are just ions that have more than one atom in it. They're kind of like a molecule, but in ionic form. Most polyatomic ions are anions. So in the periodic table you'll receive in your high school science course, they will give you a table of the most common polyatomic ions you need to know. There we go. Ionic nomenclature. If the anion in the ionic compound is a nonmetal and it's not a polyatomic ion, the stuff here, then change the ending of the nonmetal to end in "ide", as you would with molecular compounds. So for example, sodium chlorine, you change it to sodium chloride. Iron 3 oxygen, you change it to iron 3 oxide. But if the anion is polyatomic, then you leave the name as is. You don't change the ending to "ide". So for example, if I have this one, CuSO4, instead of saying copper sulfide oxide, I'd call it copper, and then find the polyatomic name of the SO4, which is sulfate, right here. Therefore, CuSO4, we will call it copper sulfate. When writing ionic compounds, because if you recall, transition metals have more than one charge. When writing the name of transition metals in these compounds, you will need to include the name of the charge. So for example, if you look here, I wrote iron 3 oxide because the iron ion in this compound has a charge of 3. But another form the iron can have is to have a charge of 2. So you need to clarify in your compound which charge it has. Now in ionic nomenclature, so unlike molecular nomenclature, you don't need prefixes for your compound, because ionic compounds will always form with the same number of atoms. So for example, ionic compounds can have C3H8. They can have the same elements in their compound, but different amounts of that element in said compound. In ionic compounds, for example, a compound with copper sulfate, it will only form a compound with 1 copper and 1 polyatomic ion of sulfate. It will never form like a compound with 2 coppers and 1 sulfate. Okay, so here I wanted to show you guys an example of how to do ionic nomenclature. We have Li and F. Li is, we'll call it lithium, and then we change the anion name, which is fluorine, ending to "ide. So this will be called lithium fluoride. And this one, again, first one, lithium. And then we change the second one to the second ending to IDE, so lithium oxide. And if you recall, for ionic compounds, you do not need any prefixes. This one, oopsies. All right. First atom, hydrogen. And then the second one, oopsies, I can't spell. Second one is a polyatomic ion. So we will look for its name on the table of common polyatomic ion thingy. And SO4 is sulfate. So this thing is called hydrogen sulfate. Now, I wanted to talk about, let's see, what was I trying to talk about? Because ionic compounds always form the same compound, you will need to know how many of each element they will have in their compounds. So for example, if I didn't give you the chemical formula for lithium oxide, and I gave you instead the word equation, so this thing, and told you to write out the chemical formula, you will need to figure out how much of lithium is in that compound and how much oxygen is in that compound. You can do so by finding out their charges and balancing it. So for example, lithium, if we look on the periodic table, has a charge of +1. And oxygen has a charge of -2. They actually don't write that on your periodic table, so you will have to memorize, sort of memorize the charges of the nonmetals. All right, but oxygen has a charge of -2 and lithium charge of +1. So if we write LiO, this is an unbalanced compound. To balance it out, since the oxygen has a charge of -2, we will need a charge of +2 from the lithium. Therefore, we need 2 lithiums to balance out and neutralize this compound. There we go. So information about ionic compounds, they can form precipitate. So in chemical reactions with ionic compounds, they will form precipitate, or solids. So let's say you have like 2 chemical solutions, liquid chemicals, and you pour them together, a solid will probably form in their reaction. Ionic compounds can conduct electricity in solutions, which we call electrolytes, like that drink thing, if you know what I'm talking about. They will always contain both cations and anions, which are metals that are the cations. The metals include the transition metals, and they will always contain nonmetals, metals and nonmetals. Ionic compounds, unlike molecular compounds, form ionic bonds, which means they transfer their electrons to each other. Whereas if you remember, in molecular compounds, they have a covalent bond where the elements share their electrons to get that full valence shell. Ionic compounds also have a high melting point, which is what the MP stands for. They're also soluble to some extent, so you can dissolve them in water to a certain extent, and are typically solid at room temperature. Moving on, acids and bases. First of all, let's talk about water. Water is polar, which is the opposite of nonpolar. Wow. What this means is that water is kind of like a magnet. It has a slight positive charge and it has a slight negative charge. I forgot which side has the positive charge. Oh, there we go. Hydrogen has a slightly positive charge in the water molecule, and oxygen has a slightly negative charge in its molecule, in the water molecule. This polarness of water allows water to have adhesion, which is when the water is attracted to other polar objects. So, for example, let me think. I can't think of an example, but let's move on. This also allows water to have cohesion, which is a form of adhesion, except water where water is attracted to itself. So for example, if you see here, we have a water droplet. Because water is attracted to itself, it forms a droplet rather than like just being flat. Let me think of a way to put this. Okay. You know how you can fill a cup of water to the very brim and then maybe, that's not what I'm looking for. Okay, now I have an example. Adhesion. The water has adhesion. You see here, those water droplet, it's not rolling off the leaf, it's sticking onto the leaf. Adhesion, water is attracted to other objects. Cohesion, water is attracted to itself. These water droplets, they form, if you've seen, smaller water droplets sometimes combine to form a bigger droplet. Basically, the water attracts each other. There we go. All right, and then if you've heard of hydrophobic things, hydrophobic chemicals, these are things that are non-polar, and these things repel water. The polarness of water is what gives water its strangely high melting point for such a small molecule. Now, quoting Tony, your other instructor who is not here, from in my Bio 20 IB class, he once said, "Water is crazy," and that is true. Now, ice. Ice is honestly what makes water crazy. Ice is less dense than water. So if you've noticed, when you have a cup of ice water, the ice floats on the water instead of sinking. Normally, for objects, when in their solid form is usually more dense than their liquid form. So water is the only molecule that becomes less dense when it is in its solid form. Why does this happen? Because when frozen, water molecules spread apart instead of condensing together like other molecules. They spread apart and form a six-sided ring in an organized manner. So here you see the organization of what water looks like in its different states. When water is in its liquid form, its molecules are just doing whatever, okay? In solid form, they spread out and form these hexagons. Cool, right? It is cool. Acids, they have a pH of less than 7. pH, by the way, stands for power of hydrogen. They're also soluble in H2O, so soluble in water, which means they are aqueous. Oh, all acids are aqueous. I will expand on that later. Acids can conduct electricity, and they have a sour taste. So think of vinegar, which is an acid. It tastes sour, right? What else is an acid? Lemon juice, there we go. Acids cause indicators to become red. So if you guys are familiar with indicator paper, when you put them in an acid, it will become red. So one way to remember this is that acid ends in D, and so does red. And think when paper becomes red, it means it's an acid. In Science 10, you will perform labs to see if something's an acid or a base. Acid has the ability to neutralize bases, and they often produce hydrogen gas. So for example, acid can corrode metals. This chemical reaction produces, when acid corrodes metals, it is a chemical reaction, and this chemical reaction produces hydrogen gas. Oh yeah, I said I was gonna expand on the aqueous part. Okay, acids are liquids. Acids, okay. Let me give an example here. Let's say I have hydrochloric acid, so HCl or whatever. Hydrochloric acid. Oopsies. What am I trying to say? Okay. I said that acids must be aqueous. If an acid is not in aqueous form, it is not an acid. So for example, I have hydrogen chloride. If hydrogen chloride is aqueous, it becomes hydrochloric acid. But if it's in like solid form, it is not an acid. It's just called hydrogen chloride. Don't ask why, but acids are only acids if they're aqueous. A base. Bases have a pH of greater over 7. They are also soluble in water. They have an ammonia smell, which is, I don't know what that smells like. I think I remember one of my teachers saying it smells like pee, but I actually don't remember, so don't take my word for it. They have hydroxides. Bases will contain hydroxides. Bases also conduct the electricity and they taste bitter. So for example, if you ever ate soap like I did when I was 7, soap tastes bitter. Bases are also slippery. I should mention that soaps are a base. So remember, if you've used soap before, and I hope you have, it is slippery. Wash your hands, guys. Stop the spread of COVID. Bases also neutralize acids, another name for bases can be called antacid. Bases also dissolve grease, so hence your soap, and they turn indicators blue. To remember that bases turn indicators blue, just think base starts with a B and blue starts with a B. Now, if you notice here on the right of the slide, I put a giant Tums photo. I don't know if you guys have seen this thing, but I think it's a commonly prescribed medicine for stomach issues for something. Ooh, someone's typing in chat. Yeah, okay. So basically, the stuff in this Tums, they're antacids. So when you have this treats acid reflux. And if you remember, bases, or sometimes antacids, they neutralize acids. So to treat your acid reflux in your stomach, they will use bases. And thus, ta-da, antacid. Moving on. Yeah. pH scale. So if you remember, I said acidic stuff turns your indicator red, and then bases turn your indicators blue. Now, pH is measured to a power of 10. What I mean by this is that if you say something has a pH of 7, it means it has a hydrogen concentration of 10 to the power of -7. If you say something has a pH of 6, it means it has a hydrogen concentration of 10 to the power of -6. Another way to phrase this is that something with a pH of 6 is 10 times more acidic than something with a pH of 7. Neutralization creates salt and water. So when acids and bases are mixed together, their chemical reaction makes products that are a water and a form of salt, usually. Random key term that you need to know, a buffer. A buffer is a substance that keeps the pH of a solution pretty constant. All right, acid-base indicator. In school, some common acid-base indicators you'll use will be phenolphthalein and indicator papers. Acid-base indicators are a chemical used to determine if a solution is an acid or base. So for example, phenolphthalein. There we go. Now, activity. I mentioned earlier you will need access to Google Slides for this lesson. So if you go into your Pilot Science 10 folder and go into lesson 3, you will find something called breakout room. Click onto it. Go into it. I'm gonna wait for people to show up on the breakout room. Oh, hi, you're here already. That was fast. Okay. For this activity, choose one of the slides here, one of the slides 2, 3, or 4, and then work on it yeah. Originally, I was going to assign each person here who arrived to the class a slide, but there's only one person. So shout out to Zainab. So choose a slide, work on it. You have like 5 minutes. Wait, do you have editing?
I can't edit it.
Oh shoot! My bad. Let's see. I will now give you live editing access because I forgot to edit everyone. I will literally give editing access to more people. Refresh the page and see if you can edit it. Edit it now.
Yeah, it works now.
Okay, I am going to pause recording. Okay, for those of you traders who are watching on recording, basically what happened was we had Zainab here soloed all the activities, and then we went on break. And now we're back from break, and we are now continuing the lesson. All right, oops, click. Acid nomenclature. In acids, in the chemical formula of acids, you will always find hydrogen. And in a previous slide, I mentioned that they are always aqueous. And if the acid is not in aqueous form, then it's not an acid. Here I have the exact same example I used beforehand. HCl aqueous is an acid, so hydrochloric acid, but HClS is not. So that's hydrogen chloride. How to name an acid. If an ionic name, if the ionic name, so if you follow the ionic nomenclature process for the acid, and it's a hydrogen blank, something that ends in "ide," then you will call it hydrochloric acid. Hydro blank, and instead of the IDE ending, you change it to IC acid. So, for example, the ionic name of HCl is hydrogen chloride, and then you change the ending to IC, so it becomes hydro, and you put, instead of saying hydrogen, you say hydro. So it's now, instead of hydrogen chloride, it's now just hydrochloric acid. I should give more examples. Yeah, I will give more examples here. Let's say I have HS or something. Okay. It's probably not balanced, but hydrogen sulfide, you change the hydrogen to hydro, and then sulfide's ending to IC, so sulfuric? No, sulfur special, you call it sulfuric. You change the ending of sulfur to IC, so it's sulfuric hydrosulfuric acid. Now, if the ionic name is hydrogen something and it ends in ATE, so for example, we have a compound which, we have a compound, there we go. We have a compound where the anions of polyatomic ion that ends in ATE. You will change the ending of the polyatomic ion to end in IC, and then you won't include the name hydrogen at all. So for example, this is hydrogen sulfate. The SO4 is called sulfate in its polyatomic ion form, and it ends in ATE. You will get rid of the hydrogen name, just don't say hydrogen at all. And then sulfate, changing the ending to IC, and it is now called sulfuric acid. Sulfate, sulfuric. Yeah. Now, if the ionic name is hydrogen and has a polyatomic ion that ends in ITE, so for example, hydrogen sulfite, you will get rid of the word hydrogen in its acid nomenclature and change the ending of the polyatomic ion to end in OUS, followed by the word acid. So hydrogen sulfite in its aqueous form or acid form will become sulfurous acid. Let me see if I can give more examples on each of these. Let's see. Let's make another example so you can have a better idea. Let's say we have magnesium nitrate or something. Yeah, sure. Does that even, no, that's not right, sorry. Hydrogen nitrate. In its non-acid form, it's just called hydrogen nitrate, but in its acid nomenclature form, again, get rid of the word hydrogen. So instead of hydrogen nitrate, we now have nitrate. Change the ending of nitrate to IC, replace the ATE with IC, and it's now called nitric acid. If we do the same with this, so let's say I have H nitrite. This is like a 2 or a 3 here. I don't remember the number. I'll say it's a 2. Hydrogen nitride. Again, in its acid form, get rid of the word hydrogen, so it's just nitrite. Change the ITE to OUS, and it is now called nitrous acid. Moving on. More on acid nomenclature. They're like molecular compounds where they have common names. There are also acids with common names, and they are exceptions to the acid nomenclature process. These, you don't need to remember them, unlike the molecular ones, but to give you a general idea, their compound usually, you'll see that their compound usually ends in COO. So some examples of acids with common names are acetic acid, benzoic acid, and oxalic acid. So if we look at the chemical formula for acetic acid, which I'm just going to Google because I don't know it. Oh, there we go. It has COO. There we go. Yeah. More. Base nomenclature. Bases, they don't have a special naming procedure because they're not as cool as acids. You can identify bases by, so to know if something is a base, look in the compound, just look for a metal or ammonium ion, which is a polyatomic ion, and then its anion should be a hydroxide, so an OH. For example, an example of a metal is sodium, an A, and then if it has OH, it is a base. Wow. Another example of a metal, magnesium, and it has an OH, it is now a base. I'm just gonna keep going. Iron, this is iron. How do I turn it into a base? Add OH, it is now a base. I need to balance that, sorry. Fe, and for it to match the charge of iron, it should be something like this. And this should be in subscript, but I can't be bothered to do so, it's too much work. None of these are balanced properly, by the way. Like the charges aren't neutralized in this form. Moving on. Balancing equations. Okay. First, before we do the actual fun part, not a fun part, it's just math, of the balancing equations part, we're going to look at the 5 common chemical reactions. So, simple composition, decomposition, single replacement, double replacement, and combustion reactions. There are many more types of chemical reactions, but these 5 are the only ones you will be studying in Science 10. Wait, no, and one more. Acid-base neutralization. It is now 6. Wow. And you don't have to write these down right now, just because I'm addressing them more in the following slides. So let's take a look at simple composition. Simple composition is the reaction of 2 or more elements to form a compound. Here we have an example. So we have magnesium reacting with oxygen, and it forms a compound to make a magnesium oxide. Wow, I can give more examples. Sodium. Darn it, I'm in subscript. This font is tiny. Sodium and fluoride, why not? can become, oopsies, they combine to create sodium fluoride. Okay, yes, sodium fluoride. And I need to write their charges, but I mean their states, but I can't be bothered to do so right now. These are the states of the compounds. I will explain more on why we need to write states later. Decomp, or yeah, decomposition, which is the breakdown of a compound into its elements. So here we have an example. Let's say hydrogen sulfate, I think this is, oopsies, decomposes into its element. So H2SO4 will become, I need an arrow. There we go. Hydrogen gas and sulfur. Wait, I'm being clay for 0.8 gas, I think. Oopsies, that should be lowercase. And oxygen gas. So, Zainab, do you know why I have these numbers after the element? There we go. Why aren't these atoms by themselves? Why do they have numbers by them? Why are they in molecular form? No, I cannot hear you, Zainab. Oopsies, I did not mean to type in the chat. Zainab. I still can't hear a microphone, so are you able to type your answer in chat instead? I'm going to keep talking about the question in the meantime. Oh, okay, Zainab is correct. They are molecular elements. So hydrogen sulfate decomposes into hydrogen gas, which forms as an element of H2. This should be in subscript. All of the numbers following my elements should be in subscript. So like this, but so much work to make them all into subscript, so I don't pretend they are all in subscript. Again, so going back to what Zainab said, they're molecular elements. And if you remember your molecular element acronym, or at least that's what I use, you could also use what Tony uses, what he calls 7 of 7, to remember the molecular elements. Let's give an example of a decomposition where there's no molecular elements, where the atoms won't form molecules when they're decomposed. Let's have sodium like fluoride, why not? Again, sodium fluoride, it becomes sodium and fluoride, wow. It decomposes. Since these are not molecular elements, they will not have numbers after them. They will not form molecules in their natural elemental form. Wow. Okay, something else I need to mention about balancing chemical equations or writing chemical equations, we don't use an equal sign, we use an arrow sign instead of an equal sign. But drawing an arrow on here is so much work. So I'm just gonna like write equal signs instead for the following questions. Oopsies. Single replacement, your third type of common reaction. An ion, you can write, or SR for short, if you want. Ionic compound reacts with an element someone is typing in chat. Okay, Zainab, thank you for correcting me. Has a subscript up. Wait, I bring clay for, yeah, it does. Oopsies. My bad. Thank you for the correction. But that, yes, it has a subscript of 2. See how I passed Science 10 is beyond me, guys. And how I'm not failing Chem 20 is also beyond me. But single replacement. Ionic compounds react with an element to form a new ionic compound and a new element. So think a compound of A and B reacts with element C to form a compound of A and C and element B. So for example, let's say iron 3 oxide reacts with chlorine. So Fe3 oxide. To balance that, we'll just write this reacts with chlorine, which has a molecular element, which is a molecular element. So it has a subscript of 2, and it creates iron chloride 2 or something. 2, 3, 3. Iron chloride 3, I think. Okay. And oxygen gas. There you go, an example of single replacement. So what I've written up here are skeleton equations. Oh my gosh, I should balance these. I talk about balancing chemical reactions. I haven't balanced them at all. All right, so how to balance a chemical reaction. This we call a skeleton equation. To make it a not skeleton equation and have it balanced. Look here, we have 2 irons, and then after the reaction product, we only have 1 iron. This is unequal. So to balance that, we're gonna make it so that that means after the reaction, there should be 2 of this compound, because there's 2 irons. But because there's 2 of this compound, that means there's 2 of the Cl3s, which means there's 6 chlorides in total. But on this side, on the left of the equation, we only have 2 chlorides. How do we balance this out? We're going to use 3 chloride elements so that it balances out. Now we have 6 chloride atoms here and 6 chloride atoms here, as well as 2 iron atoms here and 2 iron atoms here. Oh, we now have an issue. The oxygen, the last one. We have 2 oxygen atoms here and 3 oxygen atoms here. But even if I increase the number of oxygen atoms, it will not equal an odd number. What can I do? I can double this element compound on this side. And in turn, I will have to double everything else. So I now have 2 of 2 irons. Therefore, I have 4 irons. Now, because I have 4 irons, I need to balance this side. We now have 4 of this compound, and now we now have 3 times 4, sans 3 times 4, 12 chlorines. 12 divided by 2 is 6. So 6 of the 2 chlorine atoms, they now have 12 chlorine atoms on both sides. Now, how many oxygen atoms do we have on this side? 3 times 2 of this molecule, so 6 oxygen atoms, divided by 2 is 3. We now have 3 oxygen elements on this side. This chemical equation is now balanced, where there's an equal number of each atom on both sides of the equation. Now, something else you're supposed to do when balancing chemical reactions is to write their state. So for example, iron oxide will be a solid. Why, I will explain in a later slide. This is a gas. And you will just need to remember that chlorine naturally forms gas. That's something you have to memorize. This will be a solid, and oxygen obviously naturally forms a gas. I will show you this in proper notation so you have a better idea of how to properly write this. Your states are written in subscript, but the number of that molecule you have, the amount of molecules you have, the number in front, is not in subscript, but the other numbers that show how many of that atom is in the molecule or the state should be in subscript, like so. Yeah. Yeah. And then in proper notation, this should be an arrow. There we go. So if you're doing a chemical reaction homework test question on paper, this is the correct notation we need to write it. Moving on. Double replacement, or DR. Two ionic compounds react to form two new ionic compounds. For example, a compound with A and B reacts with a compound with C and D to create a compound with to create two new compounds with A and D and C and B. So for example, here we have copper sulfate reacting with iron oxide. So let's say the copper is A, sulfate's B, iron C, and oxygen's D. B trades place with D, so copper trades place with that. Iron, wait. Basically, you move the stuff around, all right? Just, they switch anions. The two compounds switch anions. There we go. So the anion of the iron oxide, which is the oxygen, moves to the copper, and it now becomes copper oxide. The anion of the copper sulfate, so the sulfate, moves to the iron, and it now creates iron sulfate. These are the products of this reaction. Also, if you look at this equation is actually already balanced because there's only, yeah, this equation is already balanced. There we go. Your fifth type of common chemical reactions, combustion. So it's when an element or compound reacts with oxygen to produce metal oxide. Usually what we mean by reacting with oxygen means it's just set aflame. All right. Your element or compound is burned to produce metal oxide. Sure. In Science 10, what you will usually do is in your combustion reactions, you'll usually have hydrocarbon combustion reactions. These are the kind of combustion reaction questions they will give you. For example, a hydrocarbon. Okay, first I should explain what hydrocarbon is. Hydrocarbon is an element, a compound with hydrogens and carbons. Wow. And then some other stuff, usually oxygen. Let's say we have an example of C6H12O6, and if we remember, its common molecular name is like either glucose or sucrose, okay? Something like that. It is burned with oxygen. It then creates carbon dioxide and water vapor. All hydrocarbon combustions will always create carbon dioxide and water vapor. That's pretty much what you need to know for combustion reactions in Science 10. You see a hydrocarbon compound with oxygen, that means its results are carbon dioxide and water, that's all. And then you just need to balance it. Oopsies. Sometimes combustion reactions can be confused with single replacement, or what is that? Simple composition. Oh, that. So the composition reaction. Because, for example, Fe and oxygen, this can be confused with composition, where it's two elements reacting to create one compound. But I think for this, you can call it both a combustion reaction or a simple composition, but the teachers will prefer if you call it combustion, since it's combining with oxygen to create iron oxide. But expanding on combustion reactions, if you are burning something that contains sulfur, sulfur dioxide is produced. If the object being burned, the chemical or the compound contains hydrogen. So for example, in a hydrocarbon combustion, there will be water in the products. If your combustion contains carbon, then CO2 will be produced, as seen in this example. Fine. Moving on. Now I talk about balancing chemical equations. So balancing chemical equations uses the law of conservation of mass, which is just like something along the lines of mass can't be created or destroyed, I'm pretty sure. Now, these chem equations kind of have two forms. We have the word equation and the chemical equation itself, where the chemical equations use the chemical formula to show the equation, and the word equation just uses the English language to write out the equation. So these two are the same chemical reactions, but just written in the two different forms. Here in the written form, we have iron 2 oxide decomposes into iron metal and oxygen. Chemical equation form, FeO becomes iron and oxygen. Well, you need to be able to convert between a chemical equation and a word equation. This is a common test question where they give you a word equation and you have to balance the chemical equation, write out the chemical equation itself, and then balance it. And you also find this in your homework. When balancing chemical equations, always remember to write the states, these things. And then I said I will explain how to know the states of the compounds. Ionic compounds are typically solid, so you can usually label them as solid. Molecular compounds, you will have to do either a guess, or sometimes they will tell you in the word equation itself. Maybe I should give an example. Sure, hydrogen chloride. Oh, there we go, I know. Aqueous, no. Solid hydrogen chloride. Reacts with something, okay? Usually in a question with a molecular compound, they will tell you the state it is in, so you will know how to write it. But if they don't tell you, well, too bad. Do an estimated guess and hope for the best. Okay, breakout 2. Go back to that breakout room. Back to the breakout room in the Google Drive. Activity 2. We are to solve and identify the type of reactions in the following slides. So since Zainab's the only one here, she will have to do all the slides solo again. I will pause the recording so she can do her work. Yeah. Pause recording. All right, so Zainab again, props to her, soloed the second activity as well because the rest of you didn't show up. Anyway, moving on. Acid-base neutralization. Why did I put that after the balancing chemical equations? This is your last type of reaction. Yes. So you have an acid combined with a base, which will create water and a salt. This is not it. Where did it put it? Let's say, for example, I have sodium hydroxide, and if you remember anything with a hydroxide, it's probably a base. It's aqueous, and it combines with hydrochloric acid, which is my favorite acid, guys. Why? I don't know, it just is. Hydrochloric acid to create. And in the case of acid-base neutralization, it's a lot like double replacement. So we take the anion of this one and it combines with the cation of this one to create HOH, which is water, and we take the sodium and we combine it with the chloride of this one, so it becomes sodium chloride. I don't know what state this is. Oh, it's probably solid. No, I don't know. It could be aqueous or solid. Oh, right. I should show you guys how to know if something's aqueous or solid. I completely forgot about that. Okay, water is a liquid. Wow. Now, moving on. The number stuff you need to know in chem. So something we have in chem is called an Avogadro's number. I don't know why they taught us this in Science 10, but you technically use it more in Chem 20 or Science 20 than you do in Science 10, but they just tell you the number anyway. So what Avogadro's number is, it's like a unit. So if you say I have a dozen eggs, it means I have 12 eggs. Avogadro's number is called a mole. And so if I say I have a mole of eggs, it means I have 6.02 times 10 to the 23 number of eggs, which is an awful lot of eggs. Why is it this number specifically? Well, there is something special about the Avogadro number in large periodic table. Okay, yeah. 6.02 times 10 to the 23. Why is that number special? If we look here on the periodic table, you guys see the masses of the elements. There we go. Now, 6.02 times 10 to the 23. I need to keep reminding myself. Why this number is important? Basically, if we have 6.02 times 10 to the 23 amount of that element, the weight of that will be equal to its atomic mass in grams. So to explain it more or to give examples, the atomic mass shown on here is measured in atomic mass units, which is a very tiny unit. But if I have 1 mole of beryllium, 1 mole of beryllium will weigh 9.012 grams. This is useful in Chem 20 when you're doing like advanced reaction stuff, I guess. It's not advanced. So let's say an example of a Chem 20 question where you will need to use the mole would be like, you have 5 grams of beryllium. How many molecules of beryllium will you have? And you will use like the mole, you will use moles to figure out how many molecules of beryllium, atoms of beryllium you will have from how many grams, from the grams amount they give you. Cool, you don't really need to know this, so whatever. Moving on, scientific notation. It is used mainly in significant digits, which we call sigdigs for short, or some people say sigfigs, significant figures. You'll learn this in the next unit. So for example, in scientific notation, where 1 unit left of the decimal is multiplied by 10 to the power of associated decimal places moved. That definition makes no sense. But example, 200 will be converted to 2.0 times 10 to the 2, which is equal to 200. You will have only 1 digit to the left of the decimal place, and you will multiply it by the associated number of decimal places moved. Oops, I keep. 2,345 equals 2.34 times 5 times 10 to the 3. So this is scientific notation, the one on the right here. Why do we use this? You'll find out in sigdigs. Okay, hi. End of lesson, guys. Great lesson with only 1 person. Next unit will be, we have finished the chem unit in a rush, but next is physics unit, and Tony will be teaching that unit, who has dipped this lesson, that instructor. All right, bye guys. Bye-bye, fun lesson. I'm gonna end the recording.